Okay, so here's a quick rundown of what Unit 6C is all about, aka coordinate geometry proofs. The first formula we're going to talk about is the distance formula. It allows you to find the distance of segments. Now, if segments are horizontal, you could easily just count them. So 1, 2, 3, 4, 5, 6, 7. That would be 7. This one would be 1, 2, 3, 4, 5. But as soon as it's diagonal, things get a little bit more difficult, because how do you count a diagonal segment? The distance formula is given for any 2 points, such that I do x1 minus x2 squared plus y1 minus y2 squared. This is derived from the Pythagorean theorem. So if I know t is 3, negative 2, and I know v is 1, 2, 3, 4, 5, 6, 7, 8, 5, I believe that is. 1, 2, 3, nope, 8, 4, whoopsies. 8, 4. I can apply the distance formula to these points. So it doesn't matter who's x1, y1, or x2, y2. You just make a decision and you roll with it. So I'll do 8 minus 3, square it, because it's the difference of my x's squared, plus 4, now I'm going in the same order, 4 minus a negative 2, squared. So I'm going to clean this up a little bit. Okay, so under the radical, I have 25 plus 36, which is radical 3, 4, 5, 61. Radical 61. So that would be the distance of TV. So the way that we can use the distance formula is to prove that any 2 segments are congruent. So if we want to show that a triangle is isosceles, all we're going to do is show 2 sides are congruent. So this goes ABC like so, according to coordinates. Pick which sides look like they're congruent. So it looks like those 2. So I'm going to go ahead and write down my distance formula, because that's the formula I'm going to be using. Okay, so the first thing I'm going to do is find the distance of AC. So I'm labeling my work here. A is 3, 5, C is 1, 1. So now I'm just applying the formula. 3 minus 1 squared plus 5 minus 1 squared. And I'm getting radical 20. Don't worry about reducing it. I'm going to go ahead now and do AB. If I do my math right, I should get the same distance. Okay, so I'll do it this way. 5 minus 3 squared, but then I go in the same order, 1 minus 5. Okay, so this goes to 2 squared plus negative 4 squared, which is 4 plus a positive 16. Be careful there. And you'll notice I get the same answer. So therefore, AC is congruent to AB because the distances are equal. So a triangle with 2 congruent sides is isosceles, so therefore triangle ABC is isosceles. And we're done. Okay, so for the next one, if I want to prove that something's a rhombus, I can show all 4 sides are congruent, because a quadrilateral with 4 congruent sides has to be a rhombus. So I'm not going to do this one out in whole, but this looks like it goes A, B, C, D, I believe. So all you'd have to do is list your distance formula, because I'm using my distance formula, and then I find the distances of each of the sides. So for example, I'll just do AB. Okay, so A would be 1, 2, B would be 4, 3, and I apply the formula. 9 plus 1 is 10. So, like I said, you'd continue doing this. You'd do BC, you'd do DC. Oops, I don't like my notation on that one. And then I do AD, yada, yada, yada. You should get a radical 10 for each of those. Okay, so then at the end of the day, you're going to say a quadrilateral with all 4 sides congruent is a rhombus, therefore ABCD is a rhombus. Okay, so lastly with the distance formula, this one I won't do at all, but just to talk you through the idea, if I give you, let's see, PQRS, and I want you to show it's a parallelogram, I'm just going to show that both pairs of opposite sides are congruent. So what I would do is show, using the distance formula, that PQ and SR are the same distance. I would show that PS and QR are the same distance. Okay, so this would be where all my work is. The theorem I'm using is a quadrilateral with both pairs of opposite sides congruent is a parallelogram. Therefore, PQRS is a parallelogram. Okay, the next two formulas we talked about were midpoint and slope. Midpoint is what it sounds like. It's the middle of a point. Remember that a segment bisector intersects a segment at its midpoint, and a midpoint divides a segment into 2 congruent segments. Okay, so as far as the midpoint of a horizontal segment goes, you could easily figure it out. So this is 10 long, so then 5 would be the halfway point. Okay, same thing vertically. As far as diagonally goes, you could either figure it out using the slopes. So I'm seeing I could fit 2 triangles by going down 2, over, down 2, over. So this would be your midpoint. Or recognizing the slope formula, which is just the average of the x's and the average of the y's. So I'm actually going to redraw this back in. Okay, that looks like my midpoint, right? Well, L has the coordinates of 2, 8. N has the coordinates of 10, 4. Okay, and our midpoint appears to be at 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6, 6. Okay, so when I said that the midpoint is the average of the x's, think of it this way. 2 plus 10 gives you 12. Divided by 2 is 6. 8 plus 4 is 12. Divided by 2 is 6. If it's the average, it's the middle, so therefore it's the midpoint. So down below, our midpoint formula is x1 plus x2 divided by 2, y1 plus y2 divided by 2. The only place we really use the midpoint formula is to prove that diagonals bisect each other. Because if they intersect each other at the same midpoint, they must be bisecting each other. Okay, so here's how this works. If I'm going to prove this is a parallelogram by showing the diagonals bisect each other, and this is A, B, C, D, I just have to find the midpoint of AC, find the midpoint of DB, show that they're the same, therefore the diagonals must be bisecting each other. Since I'm using my midpoint formula, I'm going to write it down. You always want to write down your formulas. Okay, so I'm going to find the midpoint of AC. Okay, so up above, here's A, here's C. Add the x's together. Add the y's together. Okay, so that would go to 1/2 and 9/2. Okay, so now I'll do the same thing on the other diagonal. Midpoint of DB. Okay, so now I'm looking at these two. Add the x's together, so 4 plus -3, 7 plus 2. And you'll notice that I get the same thing. So since the midpoints of the diagonals are the same, they must be bisecting each other. So AC and DB share the same midpoint or have the same midpoint. So they must be bisecting each other. Okay. If a quadrilateral has diagonals bisecting each other, then it must be a parallelogram. Okay, so I have this a little bit more nicely written up on my notes key, but this is the basic idea. So I go on to use my theorem. If a quadrilateral has diagonals bisecting each other, it's a parallelogram, therefore it's a parallelogram. Okay, now the last formula, so this is really it, it's 3 formulas for coordinate geometry, is slope. And the good news is, you already know slope from Algebra 1. It's the difference in your y's over the difference in your x's. Okay, so counting slopes as far as anything that is straight up horizontal, that's a slope of 0, it's flat. If it is vertical, like PQ, that's what we call undefined. So basically it's any number over 0 if you were to count rise over run. So for example, this is rising 1, 2, 3, 4, 5 and running 0. So that would be 5 over 0. LN, if I count rise over run, it looks like I'm going down 1 over 1, down 1, oh, no, sorry, I miscounted there. Let's just look at the whole thing. I'm going down 1, 2, 3, 4, running 1, 2, 3, 4, 5. So the slope is -4/5. Okay, I'll do the same thing for JK. I'm going down and over. Looks like I'm going down 1, 2, 3, 4, running 1, 2, 3, 4, 5. So that means it's -4/5 again. I'm just going to erase my work here for a second. These should look like they're parallel to you, and they are. When the slopes are equal, they will be parallel. Okay, as far as RS, I'm rising 3, running 1, 2, 3, 4, 5, 6, 7, 8, 9. So my slope is 3/9 or 1/3 if you reduce that. And going the other way, I'm going down and over, which I think my segment moved a little bit by accident, because these are supposed to be perpendicular, unless I miscounted here. Oh no, we're okay. I'm going down 6, running 2. So the slope would be -6 over 2, which reduces to -3 over 1. Okay, and if you look at these, they should look like they're perpendicular to you, and they are. So these are perpendicular. You'll notice that 1/3 looks like -3 over 1, but flipped and made the opposite sign, so negative. Those are called negative reciprocals. So on the next page, if slopes are equal, your segments must be parallel. That makes sense. If the slopes are negative reciprocals, like what we just saw, the segments must be perpendicular. So that allows us to say that perpendicular lines create right angles. So another example of negative reciprocals would be something like -4/3 and +3/4. They are exact opposite signs, and they are flip-flopped. Recall that the slope of a horizontal line is always 0. That's from Hoy. And the slope of a vertical line segment is always undefined, or sometimes we'll say no slope. That's what the U in VUX stands for. As far as applying the slope formula for big numbers, you just do change in y over change in x. So I do 27 minus 12, -22 minus 23. Notice I'm going in the same order. Okay, I figured that out, yada, 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 I get an answer. Okay, so here's how we apply this. If I want to prove that this is a parallelogram by getting both pairs of opposite sides parallel, I'm going to show those corresponding sides are parallel, or those pair of opposite sides. So that means I need to use slope. So I'll write down the slope formula. Okay, it looks like this is N, O, nope. Sorry, this is L, M. I'm labeling my own diagram wrong. L, M, N, O. Did I label that right? I'm just starting over. I'm doubting myself right now. 1, 2, 3, 4, 5, 6. Yeah, so this is L. 1, 2, 3, 4, 5. Yeah, I definitely had it switched for a minute. L, M, N, O. Okay, so I'm going to show that they are parallel. So I'm going to allow you to count the slopes. All right, so let's say I start with ON and LM. For ON, I'm rising 2, running 1. LM, I'm rising 2, running 1. Since the slopes are equal, those must be parallel. So now I'll do the same thing with the other pair. I'm going to show that those are parallel. So I'm going to do the slope of OL and the slope of NM. I'm rising 1, running 4, I believe. Rising 1, running 4. Yep. So that means I have slopes of 1/4 for each of those. So again, OL is parallel to NM because slopes are equal. So what I've just shown is that both pairs of opposite sides are parallel. So a quad pairs of opposite sides parallel is a parallelogram, therefore LMNO is a parallelogram. Done. Okay, it's a little bit trickier to prove a right angle, but not too terrible. If I'm going to prove this is a right triangle, I'm going to prove that there's a right angle, which means I need perpendicular lines, which means I need negative reciprocal slopes. So it appears that the right angle is here at Q, so I'm going to go ahead and find the slope of PQ and the slope of RQ. Okay, so again, slope formula. Okay, for PQ, I'm going down 2 over 1. For RQ, I'm going up 2 over 1, 2, 3, 4. Which reduces to 1/2. Those are negative reciprocals because they're flip-flopped and one is negative. So what I can say is negative 2 over 1 and 1/2 are negative reciprocals. So PQ is perpendicular to RQ. So what does that mean? That means angle Q is a right angle. Perpendicular lines create right angles, so angle Q is a right angle. If we have a right angle, it's got to be a right triangle. Okay, so this is the very last page of the notes. I just kind of fast forward here. These are the formulas you need to know and have memorized. Okay, slope is used to prove lines are parallel or perpendicular. Distance is used to prove congruency. Midpoint is used to prove that the segments bisect each other, which therefore create a parallelogram. Okay. These are just useful tips, so now that you know all the formulas, you can use them however you want. So let's say you want to prove a quad is a rectangle. You'd have to first prove it's a parallelogram, so by any way you want. So any of these ways listed over here. You could show the diagonals bisect each other like I did. You could show that both pairs of opposite sides are congruent. You could show both pairs of opposite sides are parallel. But if you're then going to prove that it's a rectangle, once you have a parallelogram, you could do either of these. You could prove it has a right angle, which might be what I do if I prove that opposite sides are parallel to get a parallelogram, because then I'd already have the slopes computed to figure out that I have a right angle. Or you could show that the diagonals are congruent. That would be the distance formula. So it's really up to you however you want to solve it. Another example, let's say you want to prove that something is a rhombus. Again, you'd have to first prove it's a parallelogram. Then you'd have to show two consecutive sides are congruent. So again, that would be using the distance formula. So if you had a quad ABCD, you'd have to just, or parallelogram I should say, you just have to show that AB and BC are congruent. Another way is showing that the diagonals are perpendicular. So that would be using slope. So if this was again ABCD, I would find the slope of BD, find the slope of AC, show that they're negative reciprocals, so therefore these must be perpendicular. You wouldn't have to talk about a right angle at all because that's not a part of the theorem. Okay, so hopefully that makes the notes make a little bit more sense. Like I said, just a quick rundown of all the stuff that you have to do. So let's see if we do something hard like a square. Okay, so here's an example of proving a square. This is S, this is R, Q, P. Remember that a square is both a rhombus and a rectangle. Okay, I also have to first prove it's a parallelogram. So what I think I'm going to do is show that both pairs of opposite sides are parallel. So that means I'm going to use my slope formula. The reason I'm going to use slope is because then if I already have the slopes done, I can show that these two consecutive sides have negative reciprocal slopes. So I'll get to that in a second. So I paused the video for a second so that I could just write it down. So hopefully this makes sense. I'm rising 1, running 3, or going down 3 or running 1. Okay. This work that I have right here shows that it's a parallelogram. So a quad with both pairs of opposite sides parallel is a parallelogram. Therefore, PQRS is a parallelogram. Okay, great. So now if I want to prove it's a rectangle, I'm just going to pick two consecutive sides. So maybe these two. Okay, so I'm looking at those slopes of PQ and QR and noticing that those are negative reciprocals. So I think over here, I'm going to do my work in red. I'm going to say that 1/3 and -3/1 are negative reciprocals. So PQ is perpendicular to QR. Perpendicular lines create right angles. So angle Q is a right angle. Okay, so then once you have a right angle, it's got to be a rectangle. A parallelogram with one right angle is a rectangle. Therefore, PQRS is a rectangle. Okay, I didn't have to do it this way. I could have shown that the diagonals are congruent, but I didn't feel like doing the distance formula, and I already had the slope done, so it works out pretty nicely. The last thing I have to do is now show that it's also a rhombus. So I actually can use slope to figure out rhombus too. I can show that the diagonals are perpendicular. So I'm actually going to calculate the slope of PR, which appears to be going down 1, 2, running 1, 2, 3, 4, which is -1/2. The slope of SQ, I'm rising 1, 2, 3, 4, running 2. So that's 2/1. You're now again seeing that those are negative reciprocals, so therefore they must be perpendicular. So actually, let me write this. Okay, I don't have to say anything about a right angle because the theorem is if a parallelogram has perpendicular diagonals, it's got to be a rhombus. Okay. Here's the good news. I now have a rectangle, I have a rhombus, I did prove parallelogram, I got all my bases covered, so therefore a quad that's both a rectangle and a rhombus must be a square. So I can go ahead and write that at the end. Okay, so let's say you have to prove that a quad is not something. So let's say I give you a parallelogram and I want to show that it is a rectangle but not a square. Since they gave me a parallelogram, I don't have to prove that first before proving that it's a rectangle. I went ahead and just already showed my work for proving it was a rectangle by showing that there was a right angle using negative reciprocal slopes. So therefore, angle B is a right angle. So at this point, a parallelogram with one right angle is a rectangle, therefore it's a rectangle. Wonderful. Now I have to show it's not a square. So that means I need to show it doesn't have a property that it should. So there's a couple things you could do. You could show that it doesn't have congruent sides, or you could show that the diagonals are not perpendicular. Either way, you're trying to show that it doesn't have ultimately a rhombus property. Okay. Because I haven't done it in a bit, I'm going to do the distance formula. So I'm going to pause the video for a second and then insert my work for that. All right, so I wrote down my distance formula. I found the distance of AB and BC. As you can see, the distances are not the same as they would be if it was a square. So what I can say is AB is not congruent to BC because distances aren't equal. Okay, so basically I just showed that two consecutive sides are not congruent, so therefore it's not going to be a rhombus. Okay, so I'm going to write, actually I'll write it this way. A parallelogram with two consecutive sides congruent is a rhombus, therefore ABCD is not a rhombus. So basically what I showed is it's a rectangle but not a rhombus, but by definition a square is both a rectangle and a rhombus, so therefore it can't possibly be a square. So I'll just restate a quad that is both a rectangle and a rhombus is a square. And as I said, I already just showed it's not a rhombus, so therefore ABCD is not a rhombus. All right, there's one other type of thing in this unit that I included that isn't a proof. It's more of an application problem. So something like this one. In squared geom, coordinates of G are 2, -2. So there's G, and O are -4, 2. Determine and state the vertices of E and M. Okay, biggest mistake students make is they think that this is the side of the square. It is not. If you actually wrote out geom, it could look like that, or you could go G-E-O-M. But either way, GO is actually the diagonal of the square. So I'm going to use that to help me. Things I know about the diagonals of a square. I know they're perpendicular. I know they bisect each other. Okay, so what I'm first going to do is find the midpoint of GO. Okay, so if O is -4, 2, and G is 2, -2, the midpoint would be -4 plus 2 over 2, 2 plus -2 over 2. So this goes to -1, this goes to 0, which makes sense. That looks like it would be the midpoint. Now the other thing I'm going to use is again that the diagonals of a square are perpendicular. So it looks like the slope of this is down 2 over 1, 2, 3. Okay, so that means that the slope of EM must be the negative reciprocal. So it must be positive 3 over 2. So from this midpoint, I'm going to count up 1, 2, 3, run 1, 2. So this is going to be one of your vertices. And I'll do the exact same thing in the other direction. So I'm going down 1, 2, 3, backwards 2. So this could be my E, this could be my M. And there you go. That's your square. I'm just using square properties in the coordinate geometry grid to help me out. So therefore, the coordinates are 1, 3, and 1, 2, 3. I believe that's -3, -3, if I can see that correctly. Yes. Okay, and that's the unit. That's your crash course.